Thanks. I'm a little shorter than Jason. So thanks for coming to my talk. I have a lot of material to cover today. I want to cover 3 different topics. I want to cover an open source project called S Codec, another one called Simulacrum, and then I also want to look at a lot of the functional structures that are prevalent in functional programming in Scala. And what I mean by functional structures are like type classes and data structures, maybe some techniques and patterns as well. We'll see those throughout the talk. As far as an agenda today, I'm going to use S Codec as the grounding point throughout the talk, and we'll actually tour through various type classes. We'll start with functors and monads, things people are familiar with, and we'll move into some, at the very least, like experimental territory, some things that come up in S Codec and also come up in some other libraries, but aren't like well known in functional programming literature. I got one slide about me. I've been working with Scala professionally since 2008. I work for a joint venture between Comcast and Eris Group. We build conditional access software and control systems for managing digital set-top boxes. We also do a lot of stuff with like head-end equipment and video feed equipment that deals with sending like MPEG transport streams to devices. I do want to call out that I'm not a Haskeller by nature. And so if there's one thing you take away from this talk is that functional programming in Scala is absolutely a valid and useful technique to apply, even if you're not familiar with Haskell. Not that there's anything wrong with Haskell, but I am not trying to implement Haskell in Scala. So I want to start with a brief introduction to S Codec. And so nothing's ever easy to explain. S Codec is not just a library, but rather is a suite of libraries. And it's split into, I'd say, 2 different categories. There's the primary libraries made up of S Codec bits, core, and stream, and then a set of interop or secondary modules that provide integrations between other libraries in the functional ecosystem. So for example, if you're doing a lot of work with unsigned types from Spire, there's some S Codec Spire integration. There's currently S Codec Scala Z integration, and there'll soon be S Codec CATS integration. There'll probably soon be an S Codec ACA integration for reactive streams, and there's some streaming support in the way of the Scala Z stream project. I am going to spend most of the time today in this S Codec core library because it's where the core data structures come up. So S Codec core can basically be approximated by this single slide. We have 2 really primary data types. The first is this encoder abstraction. So an encoder is a trait that's parameterized by a single type parameter A. And what it does is encodes a value of type A to a bit vector. So a bit vector is a persistence data structure, immutable sequence of bits. And it's designed to be really, really fast for the types of access patterns that is common when working with binary data. This morning in the keynote, we heard about how every library defines their own either or based data structure. So S Codec does that as well, and we have this attempt-based data structure. It's very similar to like Scala's try, but where try represents failure as a throwable, attempt represents failure with a domain-specific data type called error. It's also similar to like Scala Z's disjunction, Scholastic's OR, CATS's XOR, similar idea. Encoders also have a size bound, and we're not going to really look at that today. You'll see the size bounds throughout the slides as we look at various encoders. Size bounds basically just tell you, a minimum, maximum size that could ever be generated in a generated bit vector, the size that it could be for any given value of type A. We also have decoders. So decoders just do the inverse, right? Given a bit vector, we want to attempt to decode it. And this is where things look a little bit different from like a normal serialization framework. Because what we get back is not just an attempted decoded value, but rather we get back this pair, this decode result, that has the value that was decoded and also has some remainder. And this remainder is like any unconsumed bits that the client might want to do something else with. So a good example is if you have like a 100-bit bit vector and you have to decode a 32-bit integer out of it, you would consume those 32 bits and return the result in the remainder. And then of course we can mix those 2 together and we get the primary data type of S Codec, which is just called codec. One other thing to point out here is that unlike a lot of serialization frameworks, the encoder type it doesn't return an attempt. It's defined partially over the possible inputs of type A. A lot of the times you'll see serialization frameworks define that totally, right? To say that encoders can always encode to a value and just can, and can't, when they decode, they'll be defined partially. With S Codec, we didn't want to force dealing with numeric types like integers and unsigned integers. We didn't want to force the size limitations of those fields into the type system. We knew how to. We certainly could have had a type tag or some type of value class that represented an integer bounded between 1 and 81, 91, and then defined encoders for it. But with S Codec, it was an intentional design decision that we would rather represent that as an encoder of type int, and then allow this encode to fail with an error. And you'll see some uses of that coming up. So I'm going to do a couple examples of using S Codec, and then we'll get started with our functional structures. So just starting very simple, we have 3 case classes here, a point made up of 2 integers, a line made up of 2 points, and an arrangement made up of a collection of lines. And of course, we can instantiate that and store it into this ARR value. And one of the most common use cases for serialization frameworks, at least, is to auto-generate some binary format that lets us serialize these things, these case classes, without any input from the operator. So S Codec absolutely supports that. We can import this scodec.codecs.implicits package. And if we do that, we can immediately begin encoding our arrangement data type. Here we call this require method. The require method is sort of like calling get on an option. So it's really great for slides, and it's really great for working in the REPL. It's not so great for production code. It will throw with a very descriptive error message if something fails. But if it doesn't fail, it just unwraps the attempt and gives us back a single value. So of course, with 0 code being written, only importing this one import, we can encode our arrangement type into this 288-bit bit vector. Similarly, we can decode this bit vector and get back our arrangement type, right? So this is sort of like the lowest bar we can put in place for a serialization framework. We can control how any individual component in our case classes are serialized by playing games with implicit scope. So instead of importing the entire implicits package, if we imported everything but this implicit int codec, and then defined a different codec of int in implicit scope, here's one that encodes into an 8-bit unsigned integer field, then when we encode our arrangement, we end up with something that's only 72 bits large, right? And maybe what's a little bit different here is when we go to encode this other arrangement value, one that has a -1 in the last position there, we get this very descriptive error message saying that -1 is less than the minimum value 0 for an unsigned 8-bit integer. And it includes this path through the data structure, saying starting at the arrangement, go to the lines property, from there go into the first index of the vector, and so on, navigate its way through that structure and tell you exactly where the error occurs. So this automatic derivation support is all powered by Shapeless, and it's magical stuff. Shapeless is a wonderful library for supporting this type of derivation, but this really has nothing to do with why S Codec came about, right? If you don't care about your binary format, there are wonderful serialization tools, that you can use that are very fast, very performant. All sorts of different types that you could select. What S Codec is really about is dealing with these explicit codecs. So you've got some binary format that's defined by a standards body. In my world, I deal a lot with MPEG-2 transport streams. So I'm going to work a lot with data types that are predefined, maybe are 20, 25 years old, and I need to worry about the position of each and every single bit in a data structure. And so we wanted a very compositional-based library that lets us build these codecs in a way that keeps the encoding and decoding logic together and lets us work very algebraically with the resulting data types. So here's a very simple example. There's this data type that appears in the MPEG world a lot called a packet identifier, or a PID. It's really just an integer that's bounded by 0 and 81, 91. We can define an implicit codec for it in its companion object, and we would do that by using this uint method that comes from S Codec That gives us back a codec that can handle an arbitrary number of bits. We'll say give us a 13-bit integer. And then we have two different options. We can use like this xmap operation and basically give it two functions, a function that converts from an integer to our data type PID, just by wrapping the integer with our constructor for our PID class, as well as the inverse of that, unwrapping a PID back into an integer. And if we do that, we've successfully transformed our codec of integer into a codec of PID. I did want to point out, we're going to look at xmap quite a bit today, but an example this simple typically would be written in the syntax here in the second way, where we just call the as method, and basically ask the compiler to figure out at compile time, using shapeless, how it can go about xmapping an integer into a PID in an automatic way. And of course, in this case, it's easy because there's only one field in our case class. But if we move forward and look at some more complicated case classes, that same syntax will still work. So here's another very common data type that appears in the MPEG world. It's a transport stream header from like an MPEG to transport stream. The values here aren't particularly important. It's just a set of booleans and a few integer fields. Some of the integer fields are wrapped in case classes. And this is what a more typical codec definition would look like. Maybe not quite production quality, but at least pretty close. Here we have, effectively we laid out this codec to kind of mirror the definition of this data type in the ISO specification that defines the MPEG transport stream header. We've got this table where on the left-hand side we have the name of each field, on the right-hand side we have some data type description of what it looks like. This is not a DSL, or at least it's not a DSL in the sense of like an external DSL that's getting compiled into Scala code. Everything you see on the right-hand side in those data type columns, they're really all just codecs. Putting a string, pipe, and then another codec really just adds error information to a codec and returns us a codec. Right, so everything on the slide, there's probably, I don't know, a few dozen codecs being instantiated the first time this implicit val is computed and then cached in the companion. And then, of course, when we finish, we build up all of these individual fields, and we just say convert this to a transport stream header. And that binding of all of these individual fields into that case class, all that's happening at compile time. So at runtime, there is zero reflection, and certainly no significant overhead. There is some shapeless stuff going on here too, but that's an entirely different talk. The last example I want to give from S Codec is just one more data type building on this transport stream header data type. And I don't really need to go into a lot of detail on this one, but basically there's other more sophisticated transform operations besides our xmap transform. In this case, our case class is really simple, right? We've got a header and two optional fields. And the existence of those optional fields is going to be dictated by some value in our header. And so like the codec here is using some flat prepend operator, whatever that does. And it's using some additional combinators like this conditional one to bring in optional fields. So don't worry about what those exactly do, just the idea that there's a lot of very sophisticated transform operations available on this codec data type. So what I want to talk about today is looking at encoders and decoders and codecs and really studying this core algebra of the library. And what the talk about, or what the talk is about today is how we can get inspiration from these very basic type signatures with a little bit of knowledge from functional type classes and use that knowledge to help build a bigger and better library, to help discover new combinators in the library. Okay, so let's start with decoders. The first transform we'll do with a decoder is just a simple map operation. The same map operation we're used to from lists or options or any other type constructor. Our map operation will be defined directly on our decoder trait. I'll take a function from A to B and return a decoder of type B. So this is a little bit different than like defining map on a collection, right? When we define map on a collection, we have a value or some set of values of a given type. And we map the function over it. We apply that function to, with each value in the collection yielding some new collection. Here we're like deferring application of this function until the decode actually occurs. So like the implementation of map on decoder says at some point in the future when someone actually calls our decode function, decode with the original decoder of A, get that attempted bit back or attempted decode result back, and then map over that, reach inside the decode result and map our function over the decoded value. This comes up all the time when working with decoders. Here's a very simple use case, and we'll see this one a lot today. But we have a decoder of a pair of two integers. We just map over it, destructure the tuple into x and y, and then construct our point. And so how many people are familiar with like this type of encoding of functors? Okay, good. So even if you're familiar with it, there is a little bit of a twist here in that we're using Simulacrum. Simulacrum is a macro annotation-based code generator. It runs at compile time, and it's built on top of the Macro Paradise compiler plugin. And basically what it does is generates a whole ton of boilerplate on top of this functor definition, and it does it at compile time when the functor trait is compiled. So because like functor is annotated with the @type class annotation, we basically get things like an implicit summoning method in the companion object. So we can say like, give me a functor of list, and as long as there's one in implicit scope, it'll be returned to us. Most importantly, we get like OO style extension methods. So if we have some value of type f of a, and we have an implicit functor of f available, automatically we can call all of these methods in like an infix format. And there's a bunch of other more advanced things it provides us. But the extension methods are the big one. And we'll see plenty of examples of Simulacrum as we go through the talk today. So when we look at the definition of functor, we want to say that in order to have a valid instance of this functor trait, any implementation must behave a certain way. And we're going to constrain that behavior by a set of laws. The functor laws, we have two, an identity law and a composition law. And they're pretty straightforward to describe in text. The identity law, we just say that if we map the identity function over a given f of a, we better get back what we started with. And the composition law just says, given two functions, we can either map first the first function, then the second function, or we can compose our two functions together and map the result over our f of a, and we'll get back the same value. And so what I want to look at today is how can we represent these laws of our functor class in code. And when I was first talking to someone about this, they said, well, why would I want to? I mean, that first version seemed okay. It seemed pretty straightforward. This is my answer to that. I mean, so obviously we have an automated testing perspective, right? We want to be able to say that anybody that provides an instance of the functor trait for their type constructor f, we want to validate that their instance actually adheres to these laws. And it's important that if they were to cheat, if we had an instance of that trait that compiled, but the implementation didn't adhere to every law, we have a potential break in referential transparency. So when we have a lawful functor instance, we'll be able to do all sorts of things like compose functors together, or work very algebraically with code based off of referential transparency. And if our laws are broken, some of our substitutions that we can do algebraically will actually end up introducing errors into our program. So it's very important that we want our laws to be adhered to. But we also want a way that we can represent those laws in a very evident and straightforward way. And the functor laws are pretty straightforward to describe in text. But as we move on, there's some other laws for some of the other type classes we'll look at that are quite complicated. So having an unambiguous and precise definition of those laws is a big benefit. Not only for us as we're writing it to make sure we don't transcribe the law incorrectly from some piece of literature, but also for people reading about or trying to learn about what a functor is or some type class does, because it's very straightforward once it's encoded in the type system. However, if we want our laws to be encoded in a way that facilitates learning, facilitates understanding of what the type class does, we can embed them inside of like a test framework. So like I love Scala check, and I love Scala test, and I love specs too. And I want to use those frameworks to actually test my instances, but I want my laws separated. I want them once removed from the actual test code. So when we look at these laws, we're not seeing a bunch of test machinery. We can just see the real definition of the law itself. So this is how I want to represent laws today, and I want to start with saying that this representation is more or less the same representation used in the CATS code base, and so it's absolutely from like the CATS community. Like this is not, every line here is not something I came up with. But here's how we're going to do it. We'll have a mirror trait. So we have the functor trait defining the type class. We'll have this functor laws trait that defines all of the behaviors of the abstract operations. It'll have a implicit type class instance. So whatever our type class under test is, we'll define as an implicit val. And then we're going to use this piece of simulacrum generated magic we'll say import functor.ops._, and that's going to let us call any of the methods on our type class in an infix style. So because of that, let's look at the functor identity law. Because of this functor.ops._ import, we're able to say, given some arbitrary f of a, call map on it. Like we know nothing about f short of the fact that f has an implicit functor instance available, right? So normally we wouldn't be able to call a map function on some arbitrary value of type f of a, but Simulacrum provides us some extension methods here so we can do that. And the functor identity law ends up being pretty straightforward to represent. We can say that mapping the identity function over an f of a is equal to an f of a. But we're not actually using object equality. And this is really, really important because most, well, at least many of the functor instances we're going to generate do not and cannot have like well-behaved object equality. Anytime we have, like decoder, for instance, anytime we have a functor that's in some way suspending a computation, we're not going to be able to define object equality. So we want some way to have like this notion of like deferred equivalence. I want to return basically this fancy pair of a left-hand side and a right-hand side. We call this fancy pair is equivalent. And later on, whoever calls this law, let's say in a test framework or somewhere integrated with Scala check, we can actually do the comparison and then report if the values don't match. So this fancy pair is pretty straightforward. It's just a case class parameterized by a single type and requires the left and right to be the exact same type. And then on this fancy pair, we can define this is-equivalent method. And the is-equivalent method will say, I can compare the left-hand side and the right-hand side for equality. I can say, is LHS and RHS equal to each other according to some equivalence relationship? And we can represent that equivalence relationship with another type class. And this equivalence relationship, I'm not going to show the laws for it, but it's the same laws we know and love from like object equals, right? Symmetry, reflexivity, and transitivity. But here with Simulacrum, we can define it pretty straightforwardly. We're using another feature of Simulacrum, the @op annotation, which basically generates like an infix alias. So now we can say things like 1 triple equals 1. Every framework, in addition to defining their own either type, also defines the triple equals operation, right? Okay, so let's move on to another transform. What is the, we saw map on decoder. What do we get if we try to flat map decoders? We know what we get if we try to flat map like an option or a list, but what would it mean to try to flat map a decoder? What does that give us? So let's first just define the flat map signature. We'll define it as a method on the decoder trait. It'll take a function from A to decoder of B and return a decoder of B. So the signature is pretty straightforward. And we heard earlier in one of the previous talks about how monads are really for modeling dependencies between values, right? And that's exactly what we use it for with decoders. We say anytime we've got some field or some bit pattern, that the way in which we decode that bit pattern depends on a previous value in the bit string, we're going to need to flat map or at least some form of a monadic operation in order to access the decoded value. So in this example here, we have like this unsigned integer field that's 4 bits. And when we decode that 4-bit value, we get the value 2 decoded. And now with that value 2, we're going to limit the amount of structure, or limit the number of bits that the next decoder can see of the remainder to be just 16 bits. And that's using like this fixed size bytes combinator. The fixed size bytes combinator just limits that remainder and then takes that many bits and feeds it into whatever codec we give it. We're giving it this UTF-8 thing. So basically, we end up decoding the next 16 bits as a UTF-8 string, and we get the string OK out. and then we end up with everything post that 2 bytes out as the remainder. Okay, so flat map, the important part is the fact that we get this dependency relationship. I do want to take a look at the way flat map is implemented. The general notion here, we're going to return a new decoder of type B, and we're first going to decode with our original decoder of A. That's going to give us, we're going to use a for comprehension, and the generator here, each generator is returning an attempt. So basically, the first error is fail fast, and we'll exit with that error. But assuming nothing fails, we'll get all the way through this generator sequence, right? So anyway, the first thing we decode is with the original decoder. That gives us an A result. And remember, an A result gives us both a value and a remainder. So then we take the A result value and apply our function. That gives us a decoder back of type B. And then with that decoder of type B, we can decode the remainder from the initial decode operation, yielding the B result. So at least pictorially, it looks like that as we pass bits through this operation. And if we abstract over this notion of flat mapping and add this pure definition, we end up with the definition of a monad type class. I sort of promised myself I would never put a monad definition on a slide, so I apologize. But there is a couple things here that are interesting. One is that we're going to model the relationship between monad and functor through inheritance. And there are certainly other ways to model the relationships between monads and functors. We heard earlier today that every monad gives rise to a functor. And we see it here on the slide. The way we do that is implementing map in terms of flat map and pure. And in fact, if our monad definitions of pure and flat map adhere to our monad laws, which we'll see in a second, then necessarily this map operation, as implemented this way, will adhere to the functor laws through some equality proofs. But there's certainly other ways to model these dependencies, to model the fact that every monad gives rise to a functor that don't depend on inheritance. As of right now, I would say that the functional programming community in Scala, if I could dare to speak for the community, I would say the community has kind of coalesced on this type of pattern because it works best with implicit resolution. But that's not to say that investigating other techniques isn't a useful exercise, or that someone won't invent something tomorrow that proves to be a more useful way to represent this type class relationship. We're going to see a lot more laws for type classes. These are the monad laws as implemented in this framework. And we're also going to use inheritance here to model the relationship between the monad laws and the functor laws. And so we have 3 laws. We have an associativity law and then 2 identity laws, a left and right identity. This is the last set of laws that we're going to look at in even this much detail. The rest of the laws we pull up, I'm going to move through really quickly because their definitions themselves aren't really the important point. I'm more talking about the structure of the way we're relating these things together. But you can see they're all defined in a pretty straightforward way. Our flat map associativity, given an f of a, and then 2 functions, an a to f of b and a b to f of c. We can either flat map each function, or we can rearrange the parentheses a bit. And either way, we have to get the same result. So given this monad definition, how could we write a monad instance for our decoder type constructor? We've already implemented flat map, right? That's how we started. So we can, of course, just delegate to the flat map method on the decoder trait for that particular method. But the pure operation is kind of interesting. The pure operation, we're just given a value of type A, and we need to turn that into a decoder that decodes values of type A. So how can we do that? And it ends up being pretty straightforward, although it's maybe not obvious when you go to sit down and work this out. The general idea is that the decoder that we return will always return success. And it will always ignore the incoming bit pattern and just return it completely as its remainder. And then for the value, it'll always just return whatever value was given to it. So if that makes sense as to why that's a valid monad, great. If it doesn't, don't worry about it. To validate that this is really a monad, it's probably best to run this implementation through Scala check and run it through our laws and validate that this implementation of pure adheres to all the laws when paired with the implementation of flat map we wrote a few minutes ago. And in fact it does. So this is the canonical monad decoder. Another thing we can do with these type classes, though, assuming that we have implementations of them, of the abstract operations that are lawful, is that we can write these derived methods. So again, we saw flatten earlier today. If I have some f of a, I can flatten it into an f of a, but just by flat mapping the identity function over it. And this is cool. I use this all the time with options and lists. I can't say I run into this with binary decoding, right? I could give you some contrived example where I have a decoder of A, but it's just not a pattern I run into very frequently. Now, if I did, great. I know that I have a monad for decoder, so I know that automatically I can flatten a decoder of A into a single one. But it's just not a particularly motivating example for me. So let's look at a different derived operations on decoders. Here's a monadic version of an if statement, or an if expression, right? So a normal if expression, we'd say if some guard, that's of type Boolean, then evaluate some expression of type A, else evaluate some expression of type A. And our monadic version of that is basically just going to stick a type constructor in each of those three positions. So rather than saying if a Boolean, then A, else A, we're going to say if some f of Boolean, then an f of A, else an f of A. And it's really trivial to implement this in terms of flat map. We'll just flat map over our f of Boolean and then just implement it using a regular if then else. So what does that have anything to do with working with binary? Let's take a look at this example. Here we have two decoders. The first decodes a single bit from a bit vector. If it's a 0 bit, it returns false, and if it's a 1 bit, it returns true. We also have another decoder that decodes an 8-bit unsigned integer. And if we use this bool decoder as the guard to our monadic if method, and then in the true position, we use our uint8, but we map over the result of uint8, and we map the sum constructor. And then in the false branch, we'll just use our pure method we just wrote on the decoder monad and return none. Then what we actually get back is a decoder of, a decoder that can decode an optional integer, where the first bit determines whether or not the subsequent bits are processed or not. So if the first bit is 0, then we immediately return a none and give the entire remainder to the caller. And if the first bit's 1, we decode the next 8 bits. And because we have this lawful monad, we can work with these things algebraically, right? We can just put values, assign name aliases to sub-expressions. So we can take this definition we just wrote and just pull out and generalize it to now be a very useful combinator that we can use all throughout our library. So here we just pulled out the bool and the uint8 decoders into parameters, and now we have this very nice combinator called optional, which now can just be fed to individual decoders, and it gives you back a decoder of option. Okay, so this is a very common design pattern we see when designing the library, where we're inspired by some monadic operation or some operation from a type class, and we end up finding some very practical implication of it or use case for it in the domain that we're working within. Let's take a look at flat map again, though. So specifically, I want to look at this threading aspect. Not threading in the sense of concurrency, but threading in the sense of the fact that we start with this input bit vector, we get this result back, and we feed some remainder, which is another bit vector, into the next thing. It feels like we're weaving bit vectors throughout this flat map call. And if we look really closely at the type signature here of our method, we can perform some progressive bits of abstraction and say, first let's inline our definition of our decode result tuple, or case class. So we're going to say a decode result is really just a named tuple. So let's just forget about the name for a moment and inline a tuple definition. The next thing I want to do is forget about the name decode. Let's just erase that. We're going to lift this method into a function and just say, we'll look at decode as a function from bit vector to an attempt of bit vector in A. The next thing I want to do is generalize the name. I want to alias bit vector to just the letter S. So all I've done is replace bit vector with S. And finally, I want to replace the name attempt with the letter F. And what I'm left with is this signature, S to F of SA. And here's where you need a bit of a leap, but you can basically say that there's this something familiar here about this type signature, and basically it ends up being the state T monad transformer. And I'm not going to get into like a whole big definition of the state T monad transformer, but it literally lets us sequence functions of this exact signature. Or if we want to handle various trampolining scenarios, it's a slightly more complicated signature. But nonetheless, we can sequence functions with this signature using state T. So in this case, like we wouldn't have to re-implement flat map for decoder. We could just look at a decoder as sort of a specialized state T monad transformer. A state T monad transformer where we fix the parameters to the type class with certain things. So we're going to fix the type constructor f to the attempt type constructor, and we're going to fix the state type to bit vector. So what does that tell us? Well, it's like we've discovered something about the heart of a decoder, that a decoder really is this domain-specific fail-fast state monad. That's all it really is, right? And like that's like a really kind of deep meaning, that this isn't like some arbitrary coincidence we found, but like decoder really is that. And so I say, domain-specific, right? We fix the type, fail fast, we break out on the first error we encounter, and I say state monad because we get this sequencing behavior where we can compose or flat map together multiple of these decoders to yield a larger decoder. So that's cool, but why do we care, right? There's like an intellectual curiosity that's sort of neat, but why would this help us build a better library? And one reason is because the state monad, if anyone's familiar with it, has a bunch of really useful constructors that lets you work sort of like imperatively inside of a monadic context. So we have like this get constructor that lets us like reach in and pull out whatever the current remainder is, right? Whatever that current bit vector is, and look at it. We can replace it with a different remainder, and we can modify it. And so with, if we have this, these get, set, and modify constructors in the decoder companion object, we can write code like this. Now I'm not going to go through all the details of this, but this is more of a semi-close to production version of a codec that deals with bit patterns that are delimited by ASCII quotes. So it's a bit vector that starts with an ASCII, or let's say a hex pattern of 0x22, and then there's some number of bits until there's another full byte on a byte boundary that's equal to 0x22. And then in between, whatever bit vector was in between gets decoded with a specific codec. And so if we didn't have these state monad constructors, we could just fall back and write decode in like an imperative style. But because we have them, we can actually compute the entire decoding logic in a single for comprehension. So we're able to like reach in and then replace the remainder and whatnot. So let's move on to our next type class. How many people are familiar with applicative functors? Okay, good. Lots of people. So cool. I say here applicative functors are weaker than monads and stronger than functors. I say that because there are many more data types that we could write valid, lawful applicative instances for than we could write like lawful monad instances for. The monad laws are much stronger than our applicative laws. Or another way to put that is that an applicative is a generalization of a monad. Right? That if we look at a monad and take away some of the required structure that's required by the laws, we end up with something that's a little more general. We have this applicative functor. So the applicative functor definition will define via two abstract operations, pure and app. And app's going to look just like map, except our second argument, rather than just being a function from A to B, it's going to be a function from A to B that's inside our f-type constructor. And then we're going to make applicative extend functor. We'll define map in terms of pure and app. And then similarly, we can redefine monad now to extend applicative instead of extending functor. And we can define app in terms of map and flat map. One of the things that has always bugged me about applicatives is that I kind of have a hard time wrapping my head around this second argument. Like certainly I've seen examples where like I just magically have like this f of A to B in some context, but I can tell you I've never run into a case in S Codec where I have like a decoder of a function from A to B. I can certainly contrive one, but I find it a little irregular. And there's a bunch of laws for applicative functors. I promise we won't look at these, but just their names. We have an identity law, composition, homomorphism, and an interchange law. These are complicated. These look a lot nicer in like a point-free style, written in Haskell, but when we write it all out in Scala, they get complicated. And so I find this particularly irregular. Like I think there's some missing beauty here to applicative functors. So I want to look at them from a different angle. I want to look at something called lax monoidal functors. And I'm not going to talk about why we call them lax monoidal functors. All a lax monoidal functor is a type class that extends functor and defines two operations, pure and zip. Pure is going to have the exact same signature as before. And zip is pretty straightforward. We have an f of a and an f of b, and we're just going to put them together and get back an f of ab. Now, unlike applicative functors, here we have three abstract operations. With applicative functors, we had two. With monoidal functors, we cannot write map in terms of pure and zip. So there's something interesting about that. Applicative functors, we only had two. Let's look at the laws for lax monoidal functors. Well, there's a certain beauty here, I think. There's at least some type of relationship of these monoidal laws to our monad laws. We have a left and right identity law, and we have an associativity law. So these feel much more straightforward. And if we actually worked through what these laws were doing, I personally find these much more satisfying or at least easier to understand than the applicative functor laws. And in fact, if we start tracing through, why is this thing called a lax monoidal functor, and what's its relationship to the monoid type class, we would see that these actually show a strong correspondence to the monoid laws, which are also going to be represented with two identities and an associativity law. And so one neat thing about this representation is that every lax monoidal functor gives rise to an applicative functor. Right? So if we have a lawful monoidal, we can convert it to an applicative, and vice versa. Right? If we have a lawful applicative, we can convert it to a monoidal. So we know with decoders now in S Codec, we have a lawful monoidal. Right? I mean, we know that because we start with a lawful monad instance. From the monad, we can convert that to an applicative just by type ascription, and then we can call this toMonoidal method to now get a lawful monoidal instance for decoders. So again, what's the point? Well, this ends up being the primary operation for decoders. And we're going to see an analog to it in a few minutes for codecs that is the primary operation in all of the library. People probably heard before, when doing text parsing or looking at any type of parsing combinator library, that parsers are applicative functors, right? In the same way, decoders are applicative functors. But I think this ends up being a lot easier to motivate from an example point of view. I have two decoders. In this case, I have two 8-bit unsigned integers. I can just zip them together. Now I've got that same tuple type we had earlier, and I can just map over that to construct a point. So we filled in the question marks from earlier where we just somehow magically had a decoder of a pair of integers. Now we actually have a way to construct those decoders of pairs of integers without writing it manually. I would be remiss in not mentioning that we didn't look at any of the derived operations on applicatives, and that was on purpose because they're really complicated, right? I find that app method to be somewhat mind-bending to work with at times. But anyway, if you have one person go through and define all of the derived operations, they end up being very straightforward to use. So this same example can be implemented with an applicative just via the map2 operation, but that's relying on someone actually implementing map2 for you, right? Okay, so let's look at encoders. Encoders, remember they encode a value of a to an attempted bit vector. And the first thing I want to do with them is try to map over them. And we can't map directly. We can't map a function from a to b. And the reason why is tied up in the fact that the type parameter here is contravariant. And there's a really interesting kind of deep lesson there, some relationship or correspondence between contravariance and the ability to map or contramap. But we can implement this transform operation, contramap, that takes a function that goes in the reverse direction. Right? So instead of a function from a to b, an encoder has a contramap method that takes a function from b to a. And so like when you think about that abstractly, like how, given some f of a and a function from b to a, how could I ever get back an f of b? Like I find that to be kind of a strange concept. But in the concrete, it ends up being straightforward. If we look at the definition here of contramap, we're just saying that this returned encoder, when it goes to encode a value of type b, it's first just going to convert that b back to an a using this function that was given to us. And now that we have an a, we can just encode with the original encoder that we started with, right? And in fact, the example is the same exact example as before. We have an encoder of a tuple, and we want to turn it into an encoder of a point. And we have to give it this inverse function, the function from point back to a tuple. Like functors, we can map over, we can abstract over this ability to contramap and lift it into a type class. So this is the contravariant version of the covariant functor that we looked at a minute ago. The identity and composition laws basically look identical, except that we replaced every occurrence of map with an occurrence of contramap, and we replaced the functions that are being passed to each of the laws, into the composition law, with similar functions, just with the arrow reversed. Instead of a to b, we have a b to a. Instead of a b to c, we have a c to b. And there's lots of neat contravariant functors. So like our equivalence relationship we looked at earlier is a contravariant functor. Like Scala math ordering. If you've ever used like ordering to sort a list or something, that has a contravariant functor. And in fact, like the method exists on ordering. It's just not called contramap. I think it's called on or something like that. Like Spire's partial order, we could define a contravariant functor for. Even function 1 is a contravariant functor whose implementation is just is just function composition, which is kind of a neat trick. We can fix the output type and then contramap over the input parameter. Okay, so finally, if we put all these things together, we end up with a codec. And a codec really is just the merging of an encoder and decoder into a single type. I'll warn you, like this part of the talk is where we get into some stuff that's like not from literature. It's stuff that we've kind of found by looking at the way these things work in S Codec. And one of the comments I got when I first started talking about these type classes we're going to look at is that like, oh, well, just separate a codec into an encoder and a decoder, and then you've got all the literature support you need. It's like, yeah, but that's not the point, right? The point is like if I don't want to separate them, if from a design goal, I want an encoder and decoder to always be paired. How far can we take that? How far can we keep that binding between those two concepts and still yet get this type class support? So the equivalent of mapping we already saw. When we had codecs, remember we X-mapped, right? And when we X-mapped, when we first started the talk, we had that like PID data structure. And we said in order to convert an integer to a PID, we're going to provide both directions, like a full isomorphism between an integer and a PID. And it's pretty trivial to implement. We'll just take two functions, a to b and b to a. We'll use the inverse function in encode. We'll use the forward direction function in decode. And so just like with functors and contravariant functors, we can abstract over this ability, and we end up with this invariant type class instance. So here we have this notion of invariant functors. Sometimes in literature they're called exponential functors. Actually, I should point out, I jumped the gun a little bit. These are in literature. It's the next set that aren't in literature. But anyway, invariant functors, we can define the laws in a very straightforward manner as well. They're basically the same laws as functors and contravariant functors. We just now have twice the number of function parameters. In every place we had a map before, we now have an X map. We pass both like the forward direction and the inverse. Okay, so we end up with like this lattice. If I wanted to sound like an FP geek, and if I wanted to sound like an OO person, I'd say like a class diagram, right? But I have this relationship now from I have invariant functors. We can actually show that invariant functors, or like covariant and contravariant functors, each give rise to invariant functors that just ignore the type or the function argument that they don't need. So a functor gives rise to an invariant functor that just ignores the contravariant parameter. And we got this interesting kind of relationship between applicatives and monoidals we talked about before. So this seems promising. When we looked at decoders, we were able to find a lot of power in this notion of applicatives and monoidals. Is there something interesting we can do with codecs and this zip logic? And so here, like I don't call it zip, we call it pair with, but the notion of pair with is basically that we're going to take two independent codecs. Remember, so a codec, we're going to remember how to encode things. And we're going to zip them together into a codec of a tuple. The encode logic is really straightforward. It's just, it's sort of like an applicative encode, sort of. We're going to encode each of the two values in the tuples independently. We'll encode the first element of the tuple with the original codec of A. We'll decode the second element of the tuple with the codec of B. And then we'll just concatenate those bit vectors together, assuming that they both passed, right? That they both succeeded. And then decoding is the literal flat map that we were using earlier. It just takes the bit vector, first decodes out in A, then decodes back out of B, and then returns the tuple. So if we look at just the type signature of this function, we have something that looks very much like our zip operation from the monoidal type class. And if we were to abstract over the ability to zip these things together, what we end up with is this. And so this is a name that I sort of made up, the notion of an invariant monoidal. But basically, rather than pairing our pure and zip operation with a map function, like a monoidal functor does, we're going to pair our pure and zip operation with our xmap function. And to encode that, we're just going to say pure and zip extend from invariant functor rather than regular functor, the covariant one. The laws end up being very straightforward. Again, we're not going to look at the details, but it's a left and right identity and an associativity law. So there's some nice symmetry here. And we can even go a little bit further and pull out a type class that sits above monoidal functors and invariant monoidal functors, and just pull out pure and zip. Now, we can only do this if we can define a set of laws that constrain the behaviors of pure and zip. If I can't define laws for pure and zip, then this is just like ad hoc polymorphism, and it's sort of useless, right? So how could we define laws for this zip? Well, there is a left identity and a right identity law, and there's an associativity law, but the framework that we put together today can't quite express them, right? Because we end up with these weird shapes. Like if we were to look at left identity, we'd end up with, on the left-hand side of our equals or our pairing operation, we get this like f of some tuple unit A, and on the right-hand side, we get like an f of A. And now we want to say, like, is there some isomorphism or some equivalence relationship, let's say, between these two values such that we can say that they're semantically equal? And our type class testing, law testing framework didn't quite capture the ability to do that. But we certainly could extend it to do so, and this ends up being a perfectly legitimate type class to exist. So this is kind of interesting because this zip type class actually has laws, which there have been attempts to write zip type classes before without laws, and this is a kind of an interesting result. Okay, so for the last topic, I want to look at how we can flat map now. That's sort of the last piece when we start working with codecs. We saw that we needed flat map to handle this dependency relationship where we want to say like some fields later are dependent on an earlier field. So how can we go about flat mapping if we have codecs? Now we know we can't write a monad instance. We know we can't write a monad because we weren't even able to write a regular map function. And so if we don't have a monad, like what can we get instead? And so basically, this signature we can come up with by like just kind of looking at the types of things we're doing with flat map. Like when we looked back at this previous example here, we said, okay, well, we were reading a size field and then using that size field to figure out how many more bytes to read into the next field. And so just by studying that, we can say that, like, well, in that particular example, when we're decoding, we're going to use the decoded value to figure out how to decode what comes next. But when we're encoding, the value that's written in that first field is actually computed from what comes after, right? That number 2 was the size of the string that came after. And so we can write this method called consume, which, in addition to the A to codec B, is going to take a parameter B to A. And we'll end up returning a codec of B. And here's how we might use that to implement the same example we implemented with flatmap on decoder. The forward direction is the same as we saw before with flatmap. We're going to decode the size and then use fixed size bytes to limit how much the UTF-8 codec sees. In the reverse direction, we're actually going to take the string that's handed to us and compute the number of bytes needed to store this string. And like I kind of waved my hands here at the num bytes 4. if you have to compute the number of bytes to store a string in, you might as well just encode the string. So if we use ASCII, though, that problem goes away, right? We know we can just count the number of characters in the string. And this pattern shows up a lot. I don't have time to go through this example in detail, but the canonical example of consume is a pattern that shows up in binary protocols where you've got like a byte that sits in front of everything, and it's got a bunch of bit flags in it. And if a flag is 0, it corresponds to an optional field not existing in the subsequent remainder. And if the flag is 1, then the field does exist. And so we put all of these bit fields together, and then we have all of the optional fields, all the ones that the bits are set to high, occurring in order. And it turns out that that type of pattern is relatively trivial to implement if we have this consume operation. So like this code here, like I said, it's a little more complicated than I want to get into right now. But nonetheless, it handles that case, and it does not duplicate any information in like the domain model, the values or the types that are being returned from the codec. So like nowhere here do we have a case that is possible to represent in Scala, but is not possible to represent in binary. There's a complete one-to-one correspondence between our type and our binary here. If we looked at this a little bit differently, or came at this from a little bit different use case, we end up with this thing called flatzip. And so what flatzip does is says that like, I can't compute this inverse operation, or at least it'd be very difficult for me to compute this inverse, this b to a. So instead, we're not going to require that. We'll just ask for the same thing that flatmap asks for, a function from a to codec of b. But something's got to give, right? If we don't have the inverse, then I can't give you back a codec of b. Instead, you get back a codec of a tuple, ab. And it ends up being that you can implement flatzip in terms of consume, or vice versa. Whichever one you pick to be abstract, you can implement the other one in terms of. But this comes up all the time in binary codecs as well. And in fact, one of the first examples I showed where we had like the MPEG header format, and the MPEG header format used like that flat prepend operation. Flat prepend is actually just another version of flatzip that handles some slightly different structure. So anyway, it turns out you can abstract over the ability to consume in flatzip. The problem with the names consume and flatzip are they're very specific to the use cases that they came from in S Codec. And if we were to say like, we've got this thing called an invariant monad, and it's got an operation called consume, like that name's just a little too evocative of a use case, right? So here I renamed them to xFlatMap and xFlatMap product. They don't roll off the tongue, but nonetheless, we can abstract this operation, this ability to effectively do dependent calculations on a type constructor that is an invariant functor. And even this one, even this type class has laws represented as left and right identity and an associativity law. So wrapping up, we ended up looking at all of these type classes, and we put them in this sort of hierarchy. And so I kind of have called this right-hand side here, at least when I write about these, as like these invariant shadows. It's like this set of like mirrored type classes that they're mirroring these covariant type classes from the world that we normally work in an invariant functor world. And so anyway, the last points I had, just wrapping up, is that what I think is particularly interesting here is not like the definition of flatzip, or not the notion that we got to work with some cool sounding type classes, but rather that like practical library design can be informed by working in the concrete and the abstract. Like we started by working very concretely with like binary and bits, and like it's as low level as it gets, ran into some problems, talk about how do we transform them, and we can shift gears and work in the abstract and use that as motivation to like get past the hurdle we're at, and eventually get to like a new hurdle and move back to the concrete and see how far we can get. And I think there's something very powerful about that technique. The other thing I wanted to mention is that these functional structures are legitimately useful, right? Like again, S Codec is used for bits and bytes and for building very fast binary conversions for messaging with all sorts of different systems. And yet, like all of these functional programming structures appear throughout the library, even though they're not exposed as like surface syntax. So anyway, that's all I had. I do want to thank everybody that reviewed these slides, and if you're interested in any of the details, there's a bunch of links here, both projects as well as various reading. Any questions? Yeah.
As far as you know, these haven't had no examples of this as a functional parameter in the literature.
Yeah.
Have you thought about publishing? Seems like this might be.
Yeah, so the question was, like, if there are no examples of this in the literature, have I thought about publishing it? It's funny, I was reviewing these type classes with Paul Chiasano, and I said, like, does this thing exist? I mean, am I just, inventing something here? And he said the same thing. I took that feedback and published blog posts. Publishing in a journal or something would be interesting, but I haven't given a lot of thought, so yeah, I think that's very interesting. Any other questions? Sure, sure. All right, thanks everybody for coming.